We have a survey winner for yesterday's surveys. The giveaway is an iPad mini. Is Chris Spears from Internet 2 in the room? Chris Spears. Uh-oh, not in from break yet. All right, I have a backup. One last call, Chris Spears in the room. All right, backup winner, Joseph Berthasell from NTT.net. Joseph in the room. Tough crowd. Can I draw my own name? Joseph NTT. Should have done this before the break. All right, I have a second backup winner. Andrew Lee with Indiana University. Andrew Lee? Wow. I get an iPad mini, woo! Yeah, really, the beignets are really good out there. All right, we'll take another stab at that after a talk or two here. Maybe we'll get some of our potential winners in the room. Coming up first, we have Chris Grundemann with CableLabs. He's got to talk about the future of home networking. Chris.
Thank you. So I'm going to talk about the future of home networking and looking at kind of an incremental approach of how to get from here to that future. And looking at this, I kind of broke it into 4 steps, and I'm going to focus really on the second step because I think we're really kind of into the first step already. So the second step being the most important one because it's the next one we need to take. So I'm going to focus there and then look at what comes beyond that as well. But I'm going to start with looking at why a lot of people have overlooked home networks in the past. A couple of meetings ago, I laid out a problem statement for home networks and why they were becoming more advanced, why they were becoming more complex, and why more serious network engineers probably needed to pay attention to them. And the reason we've ignored it so far is, today you have one router, one home LAN, one ISP, and it's really, really simple, and really there's nothing going on there that's interesting at all. Maybe a user adds another router for some extra switch ports or Wi-Fi range extension, and that pretty much just works. Today with IPv4, you kind of stack the NATs, which probably breaks service discovery and some other things, having these individual NAT pools. But for basic web and email and basic stuff, it just kind of works, and it's all okay. But we see this changing over the next few years and already starting to change. One of the first things is people are starting to realize that they have information on their computers that they may not want visitors to their house, especially their kids' friends or in-laws maybe don't want to see their tax returns or photos they may have on storage somewhere. And so setting up a guest SSID so that you can provide internet access to visitors without providing them access to your home LAN and all your home PCs. And then on top of that, there's other reasons for service providers to provide services based on home routers to folks maybe not even in your home at all, right? Femtocell and wireless or community wireless services and things like that. And then you go down the list, and things like smart grid are starting to come out, which is adding IPv services to your home that maybe are not necessarily under your control. The whole range of security, monitoring, and automation, the whole SMA world is kind of blowing up and moving more and more into IP. And so you have more IP devices there and more reasons for extra routers and extra complications in the home network. Potentially multi-homing, and then the big one is, of course, IP content sharing, right? Whether you're streaming IP video from outside of the home or within the home, device to device. We're seeing more and more of this, more and more contents on IP. Telecommuting adds a bunch of additional requirements. Some corporations want you to have a separate network for your work at home, your home office. And there's specific VPN requirements and security requirements and confidentiality requirements there. And then just the very basic explosion of IP-enabled devices. So a lot of people now carry a phone and a tablet and a laptop. You may have a PC at home, and then you've got spouses and kids and friends and family that all have these devices as well. In addition to sensor networks and again the security monitoring and automation devices and a whole range of IP-enabled devices in the home. And then some of those aren't running Ethernet. They're not running Ethernet, so they'll be on Zigbee or Z-Wave or some other link layer technology that needs a gateway to be able to access the home network. And so what we see happening is this simple home network becomes a lot less simple when you add a home entertainment gateway, maybe to connect your wireless speakers and your receiver and all of those devices. And then perhaps an IP sensor gateway that then connects out to all your home monitoring network. And then perhaps there's an automation gateway that connects into a Zigbee, or again, it could be Z-Wave or Bluetooth or anything else. And then of course the extra SSIDs like I talked about. And so what you see is you end up with a fairly complex home network, multiple routers in the home. And in a lot of cases, I think users aren't even going to realize they're adding routers to the house, right? So if a particular vendor decides that they're building out the smart kitchen of the future, and in their design, your refrigerator is the gateway to all of your other appliances, then you may be buying a refrigerator and also installing a router in your home. And same thing with other things as well, where people aren't necessarily on purpose adding extra routers to their home, but probably will be anyway. So, and then the other thing is, right, home users are not all network engineers, they're not all network operators, and they don't want to be. So you have to have these additional routers, this additional complexity, without any configuration, right? Unless you want managed networks, which is a whole separate issue. I mean, why am I even talking about this, right? Why is this important? Well, there's two big reasons for home networks to be important to particularly residential broadband providers, right? And that is that failure in the home network will cause service calls whether or not it's your fault, right? So if the user can't do something based on their internet connection, even if it's a problem in their home network, they're still going to call you. And you probably won't be able to troubleshoot it. So you want it to just work so they don't have to do that call. And then having this common platform for IP services allows you to sell additional services into the home. So understanding that home networks are becoming more complex and that they are probably more important to you than you may have realized, we start with phase one of this incremental approach, which is just basically adding IPv6, right? So IPv6 is being deployed today, and in a lot of cases, that deployment ends at the customer's doorstep because their home router, their smart TV, many of the things inside the house don't do IPv6. So just adding IPv6 is a big step. RFC 6204 and then the update 6204 biz, which is in the RFC editor queue in the IETF right now, are kind of that first step to just add IPv6. But it's not enough because you end up with kind of a problem where IPv4 still has a stack NAT. 6204 biz is a really good standard, but it doesn't have any way for IPv6 to enable sub-tended routers. So that second router there doesn't have any way to get addresses or a prefix or anything from the first router, so you have an IPv4 only island now hanging off of that second router that was added for maybe Wi-Fi extension into the garage. So there's some big issues there with phase one, and so that moves into phase two. HIPnet is a solution that we've kind of worked up within CableLabs and among our members and a lot of vendors as well. It's just an acronym for Home IP Networking. And what it does is it basically looks at a self-configuring home router architecture. So it adds flexibility, scalability, being zero configuration in most cases, and just adaptable to whatever the home environment is, and using no new protocols. So to start with, when we started this design process, we looked at some common principles, right? And the first thing was what I already talked about, which is that home networks are going to become more complex, but home users are not. So it needs to be self-configuring, it needs to be able to figure this out on its own, it needs to kind of just work, right? And then the second thing that happens when we start to talk about this is a lot of people say, well, just make it all a big layer 2 domain and have everything connect to one big box. And the second principle is invoking a God box leads to religious wars, right? So if you have disparate vendors and disparate technologies and different approaches, all trying to connect through one home gateway, the likely outcome is not going to be good. We also believe that new protocols bring new problems, so solving this with the protocols that are already running on home routers is the best possible solution. And we want to base it on IPv6. IPv6 gives us some very cool tools for going into the future, but also have to support IPv4 for a very, very long time, obviously. And then once we're basing this on IPv6, we know that we have enough addresses. So, specific address conservation is not necessarily a goal. So HIPnet basically takes care of all of this. It's self-organizing using what we're calling directionless routers. It provides addressing for all the devices in the home using recursive prefix delegation, so it does prefix delegation over and over again down through the layers. Hierarchical routing is pretty dead simple and doesn't require any communication between routers. And a bonus is that this supports not only IPv6 but also IPv4 without any additional work. And we did demonstrate a working prototype at IETF 86, so it actually works as well, which is nice. So starting with the directionless home routers idea, today routers are basically, home routers are directional, right? They have a dedicated WAN port and dedicated LAN ports, and you have to plug it in correctly, right? And when you're talking about, your grandfather or your cousin or somebody who has no idea what networking is, that's actually harder than it sounds, especially when you have multiple routers and cables running around all over the place or through walls and things. it's more and more likely that these things are not going to get plugged in right. So we're going to make all ports equal and use an algorithm in the router so that it can determine which one's its WAN port and which one's its LAN ports. We're calling that up detection. So in this case, we install the second router in the middle there. He basically goes through his normal process of sending out router solicitations on all of its interfaces. And then any interface that it receives a router advertisement on becomes a candidate up interface, and up means towards the internet. And so any candidate interface is then going to start DHCP. It's going to ask for its address and its prefix. And then based on the response, it's going to determine whether or not, it's going to determine which interface it wants to use as its internet-facing interface. In this case, it's going to take the first offer and choose that as a tiebreaker and pick that as its up route. So there is kind of an algorithm here to go through. So you're going to prefer valid global prefixes, right? And then internal prefixes are going to be preferred over external prefixes, and that's for multi-homing backup, which I can talk about a little bit later on. And then largest prefix, because again, if you're doing recursive prefix delegation, the closer to the service provider you are, the bigger a prefix you're going to have to hand out to a subtended router. And then after that, it goes into basically tiebreakers, which is link type and bandwidth, the first response, the lowest numerical prefix, just to make sure that it's deterministic, but kind of arbitrary. So here's a little bit more complicated example with a few routers. So router 2 there gets added in on the left-hand side. Skipping over the neighbor discovery part, he sees 3 routers, so he sends out his DHCP request and gets back responses from all of them. R1, which is connected to the service provider, in this case, let's say he got a /56 from a service provider, and he's breaking it down on nibble boundaries, so he offers a /60. The other 2 routers got a /60 from R1, so they can only offer a /64 if they continue that nibble boundary breakdown. So based on that, R2, without knowing anything about the topology or where it's at, just based on those DHCP offers, it realizes that R1 is the proper route to the internet, picks that as up, and now that becomes its DHCP client interface. The other interfaces become DHCP servers, and it just works as a regular home router with up and down ports, LAN and WAN. It also works for rearranging the network. So if we move R4 up to the top, again, he goes through the same process of sending out router solicitations. R1, because he thinks that's his internet-facing interface, isn't going to respond actually in that case. So R4 then realizes there's the internet. R1 keeps the same up interface, but is now bumped down in the hierarchy. He's going to pull new DHCP, and everything just kind of keeps going, keeps working. So what we've basically done here is taken a physically arbitrary topology, right? Anything you just kind of plug the routers together willy-nilly, and based on this up detection, you've created a logical hierarchy. And the nice thing about a logical hierarchy is that then you can do this recursive prefix delegation. So the first router, say he gets a /56 from a service provider. He takes that, breaks it up into chunks, hands chunks down. So let's say he gives /60s down to the routers below him. They can then break that up and hand out /64s to the routers below them. And it just recurses down through. What becomes really interesting here then is you have to decide how to break that prefix up. So I'm using nibble boundaries as an example here, which may work in some scenarios, but not in all. And what I think the best way to look at how to do the prefix delegation and how to break up the prefixes is based on what we're calling width and depth of the home network. So I want to look at that real quick. The width of the home network is basically how many routers are directly attached to you. So that's your width. So in this case, if there's 3 routers connected to R1, that's a width of 3. And if you were to add 2 more routers, you'd have a width of 5. And then conversely, the depth is how many routers are connected in serial below you. So how many layers of routers below you have. So in this case, you'd have a depth of 4. So then based on width and depth, you kind of get an idea for how many routers you have to serve and how many routers they have to serve. And so in order to optimize the prefix delegation, you have to break up the prefix based on those things. So we fit the prefix delegation to the width and depth of the network. And again, we don't want to add any new protocols or any new communication between routers. So we actually just use things that we know. We're using physical port count as a proxy for width. So if you have 4 physical ports, it's unlikely that you can connect more than 4 routers directly, right? Now, it's possible, or you can add a switch and you can use Wi-Fi, you can do other things, but in the general case, right, the kind of 80% rule, most of the time you're not going to be able to connect more than 4 routers directly to a router with 4 ports. So you can use that and then base your bit boundaries on the width of the network and optimize for the most amount of depth. So you basically say, okay, if I have a width of 4, then I'm going to break up the prefix into as big of chunks as possible to be able to serve 4 routers with prefixes and then have them have the biggest prefixes possible so that it can recurse through as deep of a depth as we can. Right? At the end of this, right, when you've done this up detection, created a logical hierarchy, and then done recursive prefix delegation down through, you end up with a really dead simple hierarchical routing table. So you have a default router, that goes up, right out your WAN facing, your internet facing interface. And then the down routes are all really easy because you've handed prefixes out to these routers below you. So you've given them a WAN interface IP address, and you've given them a prefix. So if you route that prefix to that IP address, you're done. The next thing that happens that's really cool with this, at least in my opinion, is what we're using a link ID to do multiple address family support. So when you look at a global IPv6 address, you've got 128 bits. And the leftmost 48 bits we don't think a home's going to get more than 48/48, right? So the leftmost 48 bits can kind of be ignored. They're the ISP designator. And the rightmost 64 bits obviously are interface identifiers. That's the actual IP that gets put on the port. So what's interesting then is these 16 bits in the middle that we're calling a link ID. And the reason that's interesting is because then if you take a new 48 bits on the front, so say a ULA prefix, for example, and you use those same 16 bits, you've now got a prefix that other routers in the home will know that you're using because you're using the same 16 bits that were assigned to you by the router above you, who's the one routing to you. And you now have a /64 that you can use in EULA space without any additional prefix delegation, without any routing protocol, without any other communication between the routers. And the other cool thing is 16 bits works out really well. If you put it behind 10 dot, right, if you use 10/8 and you move those 16 bits down, now I've got an IPv4/24 as well. So I only have to do NAT once in the house because I've got the 10 dot space being actually intelligently routed through the home and a single NAT on the internet-facing router. And then this solution also has some basic multi-homing support. We've kind of looked at multi-homing in 3 ways. There's the special purpose IP connection. So maybe you have an internet connection that's for data, and then you also have an IP streaming connection, or you have a video provider that's doing IP directly, or something like that. And in those cases, we think that's probably going to be somewhat of a managed service. It's probably going to be something that's installed and it's configured for you. So it's kind of out of scope for what we're looking at. So you're left with the backup connection where you have 2 ISPs and one's active and one's standby, and then true multi-homing where you're doing active-active, like load balancing across 2 links. Both of these can work with this model in kind of an auto-configuration method. We focused on the backup connection because we think that's the most common case, at least today. We don't see a lot of people, again, looking outside of this room, outside of the folks in the IETF, to the regular, Joe Six-Pack user. If they're going to add a second ISP, it's probably just for backup. It's probably not, they probably don't care about actually doing load balancing across the 2. And the backup connection, that's why we did the internal versus external in the algorithm for determining which way is up. What that basically does is if there's already an active internet connection in the home and a second router connects and realizes that it also has an internet connection, it's going to use the internet connection that was there beforehand. And then if that one were to fail, then it'll take over and the tree will rebuild and you'll have a backup connection. So that's kind of the HIPnet solution, which is the second step. And then phase 3 looks at the third step, which is more efficient utilization of those links in the home. So you had this physical connections, kind of willy-nilly, this arbitrary topology. Well, maybe it's not so willy-nilly. Maybe you actually connected those together because you want to have some closer links within the home. So the HIPnet solution, just doing recursive prefix delegation and then the hierarchical routing, you end up losing some of those links, right? Which in most homes is probably okay, but if you want to be more efficient and actually use the shortest paths, you could add a routing protocol potentially in the home, RIP or a stripped down version of OSPF or ISIS, and actually be able to use all of your links and have a logical mesh that's built on this hierarchical prefix delegation. So that'd be the next step beyond. And then we can go even further than that, and there's work going on in the IETF home networking group that looks at what I would consider some of this further out stuff, some of these things that are a little bit further out that can do some neat stuff. So there's some interesting IGP enhancements, right? So one of them is to use OSPF to actually assign the prefixes. So obviously the hierarchical model, you end up wasting a lot of addresses, right? Because you're building this big hierarchical pyramid and there may be chunks of it missing, right? There may not be routers in every one of those slots. So you're using some addresses kind of for white space that aren't actually being used. With this, the OSPF to assign prefixes, they basically introduced 2 new LSAs that it can advertise the aggregate prefix for the home as well as an assigned prefix. You can actually use OSPF to assign a prefix to a router. So the router at the top of at the customer edge will actually be able to use this LSA to hand 64s directly to routers who need them, and you can use your addresses a lot more efficiently. Whether or not that's something that we need to do, I'm not 100% convinced, but it is definitely an efficiency addition. And then there's another draft within the home networking group that's using IGP adjacencies to define the borders of the network. And it basically uses, again, if you have a routing protocol running in the home, you look for neighbors, and if you have a neighbor, you realize that that's internal to your home. And if you have a connection without a neighbor, that's probably external to the home. And so then you can find these edges of the network, which may not be just your internet connection, it may be other boundaries, maybe out to smart grid type stuff, or maybe there's another part of the network that's not participating, like in the telecommunity example where you may have a home office, something like that. And then beyond that, the next step, the next thing within this kind of phase 4 further out stuff is looking at better multi-homing, right? So again, there's a few drafts within the home networking group. One is the SADR work, which is source address dependent routing, which basically looks at the source address. So if you're multi-homed, right, most residential service providers today won't accept packets with source addresses that they didn't give you, right? So if you have 2 connections and you have 2 prefixes from 2 different providers, and you send packets out provider A that are sourced from provider B's space, more than likely they're going to be dropped. And even if they're not dropped, they're probably not going to make it back. So this actually has the routers look at the source address to determine which router to send them out of, which internet connection to use, so that doesn't, you don't run into those reverse path forwarding problems. There's another draft right below that that basically uses a middle box and a multi-homing service provider to provide multi-homing. So you basically have your internet gateways and then a middle box behind them in the home that's the one that actually does the decision on which router to send it out of, which internet connection to send it out of. And then on the other side of your multi-homed ISPs, you've got a multi-homing service provider that's choosing which service provider to send the packets back on. So you've kind of got middle boxes on both ends. May or may not be something you want to look at. And then there's also this two-dimensional routing protocol, 2D IP, which basically uses source and destination. It's kind of similar to the SADR work, but it's actually a whole new routing protocol rather than just an enhancement to existing routing protocols to do this enhanced multi-homing and go beyond that. So obviously that's a kind of a long timeline of things to happen. And again, I think phase 2 is kind of the most important thing. But again, why is this important? So I think we all have kind of in our hands the future of home networks, and we have a choice here. The first choice is not to do anything, right? That's always a choice, do nothing, which in my opinion kind of leaves us at phase 1, right? We've already got the basic 6204 biz standard published, so there's IPv6 router standards out there. IPv4 routers kind of just worked. But you're talking about an increasing number of service calls as things go on, as things become more complex. Broken service discovery in the home, right? So DLNA relies on UPnP, which relies on being able to send multicast throughout the home, and if you've got these NAT boundaries, that breaks. Again, with IPv6, you only have a single router today. There's no mechanism, at least not standardized or defined, for subtending routers off of it. And then again, if you're selling these IP services into the home, you've got an unknown environment, right? So there's a lot of hacks and a lot of workarounds and a lot of things you have to guess at to decide what does that home network environment look like before I can, sell into it. I don't have a common platform. So the other choice right now is to move forward into phase 2, which in my estimation would be the HIPnet solution, which is self-configuring, gives you an actual whole home network where you're actually routing across the entire home, and service discovery works, many other things kind of just work because the routing in the home actually works, and it provides this common platform for IP services. So you have this known entity, this known quantity of what you're selling into in the home. So the reason I'm giving this talk is because I want you all to help. You can support the HIPnet internet draft. There's a link to it here. We're also planning on publishing open source code, the code that we demonstrated at the last IETF. Right now it's not quite published yet, so if you're interested, you can email me directly and I can let you know when it's available. And then of course, building a HIPnet solution. If you're a vendor, right, building your next home router based on HIPnet so that you have something that actually works in the customer's home for multiple router complex topologies. Within CableLabs, we have the eRouter specification, which is compliant with this HIPnet solution. And then, again, we also have the internet draft for kind of more just off-the-shelf routers. And what we really need is industry alignment and vendor engagement around this entire solution. Because I think, the best possible quality of what can come out of this is if everyone does the same thing, right? That's the whole point of standardization. And so looking at, having this common home IP network that just works, and not only as a service provider, you don't have to take service calls, but as a geek, you don't have to take service calls, right, from family members and friends. So with that, I'd like to open it up to questions. I rushed through it because there's always questions or someone who wants to poke holes. Maybe not today.
Thanks, Chris.
Thank you.